All right, so in this second video for section 7.3, we're going to take a little bit of a deeper look into polar coordinates. We're going to look at graphing different polar curves. We're also going to talk about how to transform polar equations into rectangular coordinate equations. So just like we have Cartesian equations, right? We know a Cartesian equation would be something like, say, x squared plus y squared is equal to 4, or y equals mx plus b. Just like we have Cartesian equations, we can also have equivalent polar equations, which we can talk about plotting. So do you have any thoughts about what r equals 4 might represent? What kind of a curve could that be? We know that r represents kind of that radius, it's that distance out from the origin, and it's saying that r is some fixed amount. Well, what curve always has a fixed distance from the origin? Well, hopefully you're thinking the circle does, right? So like if we draw a circle here of radius 4, circle of radius 4, right? Every point on that curve is a distance of 4 away from the origin. So anytime you have r equals a constant, it's always going to be a circle. And in this case, it's a circle with radius equal to 4. Okay, so what about the next one? Now, the next one is an inequality. If you remember anything about inequalities, you'll remember that when you have absolute value, this can be rewritten as a double inequality, where r ranges between values of -4 and +4. And notice for theta, we don't have the full circle, right? We're only going from pi over here, right? This is at pi to 2 pi. But r can go from -4 to 4. So if r is 4 and we go from pi to 2 pi, we get the bottom half of the circle, but because r can be negative, that allows this all, remember, just like we talked in the last video, to flip over to the other side. So it actually gives us the full circle. This is, of course, assuming the radius here is 4. And because it's less than or equal to, we're actually going to shade everything inside that circle as well, because r is going to be, it's going to be all the values between 0 and 4. So this would be, again, a circle with radius 4 and all points inside that circle as well. Okay. All right, well, let's move on to example 3 here. So example 3 says, find the Cartesian equation for r equals -8 cosine theta. So that means when it says the Cartesian equation, that means we want to put everything in terms of x and y, right? In terms of x and y. In terms of x and y. So, well, what do we have at our disposal to be able to convert things to in terms of x and y? Well, we have to go back to our formulas here, right? If we want to put everything in terms of x and y, it needs to look like different things here. So we know that r squared turns things into x squared and y squared. And we know that if we have r cosine, we get x. And we know if we have r sine, we get y. Well, let's go back and look at our equation. Do we have any things that look like r cosine or r sine or r squared? And we don't. We have an r, right? We have r, and we have -8 cosine theta. So if this was like an r squared, that would be great. Also, if there was an r in front of the cosine, that would be helpful. So what about if we were to just, I mean, we can manipulate this equation any way we want, but what if we just took and we multiplied both sides by r? Well, if we multiply both sides by r, we know the left side is r squared. See, that's helpful because we know r squared is x squared and y squared. And then if we have the other side by r, we can squeeze that r in front of the cosine. We know that the r cosine is equal to x. So now we can go ahead and convert. R squared is x squared plus y squared. Then we have negative 8 times x. So we use the fact that x squared plus y squared is equal to r squared, and we use the fact that x is equal to r cosine theta. And now we have an equation that is in terms of both x and y. Okay, and that looks to be a circle. If we were to graph that, that's going to be a circle. In fact, let's go ahead and confirm that here. All right, so if we go over to Desmos, and we were to graph x squared plus y squared is equal to negative 8x, we can see that that's a circle that's been shifted over. Looks like the center is at negative 4, and it looks like it has a radius of 4. So let's see though, so I want to show you how to graph the polar version of this. So if you want to do polar, you need to click on the little wrench over here for the graph settings, and you need to change your grid to this thing, this little button that looks like a polar grid. So if you hit that, then that allows us to see it in terms of polar, and we can go, okay, well, let's just type in r equals, what was it, negative 8 cosine of theta. There you can see we got the exact same graph we had before. You can see the purple right over the green, right? There's the purple, there's the green, it's the same circle. So Desmos will also graph polar curves. All right, let's go back to our notes. Example 4 says find the polar equation for 5x minus 3y equals 15. Well, again, we're going to use those formulas that were in the theorem on the first page of this section. So if we take our equation, 5x minus 3y equals 15, we can use the fact that x is equal to r cosine of theta, and that y is equal to r sine of theta. That should be equal to 15. And then both of those terms on the left have r in it, so we could factor an r out, which leaves 5 cosine theta minus 3 sine theta equals 15. And to get r by itself, because a lot of times our polar equations will have r by itself, that means that we now have 15 over 5 cosine theta minus 3 sine theta. Now looking at this, we should know from algebra that this is a line. So it's not necessarily obvious, but the equation we just came up here, this polar equation, is also a line. Let's go to Desmos and just confirm that. So we can type in r equals, and then we have 15 divided by 5 cosine theta minus 3 sine theta. And there's our line, that black line there, right? And that's the same line as 5x minus 3y equals 15. There's the red line, there's the black line. Okay, so let's go ahead and go back to our notes. So on the last page, we're going to explore these graphs a little bit more. We have some different common shapes, some different common polar graphs, and what their forms look like. So theta equals b as a line. That should make sense, because if theta is some constant, so beta is a constant, if it's some constant, then it's just going to follow whatever angle that's at, and it'll just go through that angle. For example, if theta was equal to pi over 3, we could come back here at graph on the first page. If it was equal to pi over 3, we could just go to pi over 3, and it would be a line that went through pi over 3. That would be theta equals pi over 3. Scroll back here. We also have vertical lines. So vertical lines have the form r cosine theta equals a. That should make sense because we know r cosine is x. So this is a line that has the form x equals a. And the same thing goes for horizontal lines. That looks like y equals b, right? Those are horizontal lines. And then we have circles. We already talked about when we have r equals a constant, that's a circle. But there's a bunch of other things here. And so one of the cool things we can do here is we can go ahead and graph some of these different curves and see what they look like. So just looking at these graphs and matching them up to the form that you see above, so we could see that 1 minus r cosine theta, that's going to be a cardioid, like number 5 here, because the number in front of cosine and the number in the front are the same. So that's a, right? That looks like this form. This is going to be a cardioid. And we'll take a look in a second at what the graph of that looks like. The next one is r plus 2 cosine theta. So now we don't have 1 and 1. The last one we had 1 and 1. Now these are two different numbers. So that puts us in the lemacon category. And because it's the cosine one, we're looking at this formula right here. So this is a lemacon. Okay. And then we have r equals negative sine of 5 theta. Negative sine of 5 theta. Well, that's going to be a rose, because now we're in that format. So this is a rose, which we'll see what the graph of that looks like. And then the last one is r equals 1 plus 5 sine theta. And what kind would that be? D. So if you're looking at that, I've kind of gone over the first three. What do you think D would be? So if you said lemacon, you would be correct. That is also a lemacon. So let's go over to Desmos and see what these graphs look like. I'm going to go ahead and clear out our previous graphs. And the first one was r equals 1 minus cosine theta. We said was a cardioid. So r equals 1 minus cosine theta. So there's a cardioid. Now these, you may be wondering, are we going to have to sketch these out by hand? This is not something that I require you to sketch by hand. This is where technology is really nice, so you can use technology to your advantage. But if I do ask for the graph, you can use this to go ahead and sketch, or you can even copy and paste this into your lab assignment if you need that. Let's go ahead and go to the next one. The next one we said was a lemacon. It's 1 plus 2 cosine theta. We have 1 plus 2 cosine theta. There's a lemacon. Okay, so it looks a little bit different than the cardioid. Notice it kind of has a little loop that goes inside the outer loop. So we would expect then D, which is also a lemacon, to look similar to that. That was 1 plus 5 sine theta. 1 plus 5 sine theta. Okay, but the sine ones go on the vertical axis. They go on the vertical axis, whereas the cosine ones go on the horizontal axis. So there's another example of a lemacon. And then the last one is a rose. And these, I think, are the coolest because they look kind of like flowers, right? So we have negative 5, what was it again? Negative sine of 5 theta. So we have negative sine and then 5 theta. And lo and behold, when we said a rose, it kind of looked like a flower. And so we can kind of play around with changing this number, right? We can make that a 7 and look at how many petals there are now. It went from 5 petals to 7 petals. We can make it 10. And so it's really kind of cool. Now, what if we make this a cosine? Well, it still looks like a rose, right? So anyway, that is the idea of graphing a polar curve. And that's going to do it for this section. Feel free again to use Desmos to help you. You have your lab assignment to work on and your homework as well. So let me know if you have any questions. Thanks. Have a great day.